Hello and welcome to this bare metal programming series where we're writing firmware for a Cortex-M STM32 microcontroller. Now this is episode 4 in the series, actually the 5th episode. And in today's video, we're actually going to be embarking on one of the big promises of this series, which is, well, we're going to be writing a bootloader. And more specifically, we're going to be eventually writing a bootloader that is able to load a new firmware over a custom protocol that we're going to write that's going to live on top of UART. And that firmware is going to be signed cryptographically so that you can only run the firmware that is authorized to run on the device. That's kind of our big goal for the final part of the series. And today we're going to make our first steps into the bootloader. This is going to be what is probably the world's simplest bootloader, in that it does basically nothing logically, but we're going to lay the kind of technical foundation for everything we need to be able to kind of split the world into our application and our bootloader. So that's what we're going to be doing today, and that's a little bit different from what we've been doing up until now, which is mainly focusing on kind of getting an understanding about the microcontroller, its peripherals, libopenCM3, and kind of how we can do things in the bare metal world to make our lives easier and to express programs in a better way. So let's take a look at today's plan in order to get a sense of what we're going to be doing. And I'm just going to open this up on the side here. All right, so the world's simplest bootloader. The goal is to get the firmware split into a bootloader and a main application. So by split, what I mean is we're actually going to have two different compiled almost projects, right? We're going to have two separate projects and we're going to compile the main application and the bootloader separately. So that's kind of where we want to be at. And by the end of this, we should be able to take our two separately compiled projects and sort of create one image that will be placed onto the microcontroller. And we're going to look at how that works. But first we should actually cover what even is a bootloader. Because this term is actually quite overloaded. So depending on which context you're in and the level in the stack that you're actually in, a bootloader can mean kind of different things. So first and foremost, it's generally the first piece of code that runs on a system. Now, I say generally because you can actually have multiple stages of bootloaders, right? You can have an initial bootloader that may live in an unmodifiable ROM. That's often the case in microcontrollers or in even more complex computer systems, that there'll be some piece of code that runs when power is applied to the system and the CPU boots. Like that first piece of code is not something that you've written. It's probably something that the manufacturer has written, and it can get things just into an initial state and ready to go over. So basically what its job is, in all cases, the bootloader's job is to kind of load up or just jump to another program. So it's kind of there to maybe do a little bit of initialization work, make sure that everything that needs to be done just to get the chip brought up is done, and then jump to another piece of code. So that's what it's for. That's why it's the bootloader, right? When we boot, we load up the next program and we jump to it. And sometimes a bootloader will also verify the code that's going to be run. So often in so-called secure bootloaders, the idea will be that the bootloader can sort of come up, it can look at the code that's going to be run, so maybe it's stored in an external piece of memory somewhere, maybe it's stored in a different memory space, and it can basically have some way of looking at that and saying, is this the code I expect it to be? And maybe that's through just there being a hash because the next piece of code is also fixed, or maybe it can cryptographically verify it using a signature. And if the code is not valid, if it hasn't been authorized, then the bootloader can just say, well, I won't jump to it, I'll stay in an infinite loop forever. And this can be used to, prevent unauthorized code from running on devices. Now, if you watch any kind of DEF CON or CCC or any of the talks out there, you'll know that this kind of stuff often doesn't really work out when you really put hackers up against devices like this. They'll usually be able to find ways around it. But these are kind of things that you will find out in the world, and that goes all the way from microcontrollers up to complex computer systems like the laptop or PC that you're running on right now. Okay, in the context of our project, a bootloader is also responsible for, say, a firmware update mechanism. So there's often the case that a firmware update mechanism will live in a bootloader. And the reason that is the case is because, well, if you are able to store your bootloader separately from your main application, that means that while your bootloader is running, you can actually modify that main application. And if you're running from your main application, obviously you can't overwrite the bytes that you're executing. I'm sure there are ways to do it, but that sounds really, really difficult. And you'd have to do it differently every time you updated the firmware. So the idea of a bootloader can also be that when it boots, it's kind of looking for the possibility of updating the firmware. Maybe that's by holding down a separate button and then sending some bytes over a communication protocol. That's often what you see if you update firmware on things like Arduinos or ESP32s. You have to hold down a boot button while you apply power, and that will kind of put it into a firmware update mechanism mode. So that's kind of what we're also going to be looking at. Our bootloader is going to come up, it's going to be looking for the possibility of updating firmware, and it's going to be responsible for receiving that firmware, checking that it's valid, and eventually changing the execution from the bootloader to the main application. So that's kind of what a bootloader is in short. It's actually not that complicated. It's basically just a program whose responsibility it is to load another program. Okay, so what are we going to actually do today? Well, actually, before we do that, let's think about how we're going to split this up, how this is kind of going to break down. So I have a diagram here. So this is our flash memory space. And you'll recall that flash memory, it goes from this sort of 0800,000 number here in hex. It goes from this address up to, goes up to 87FFFF. And we can see that if we look into the data sheet for this chip, and you'll see it if you look in the data sheet for your own chip, what that flash memory actually extends to. Here we have the memory map. And if we scroll down here, you can see this is the sort of broad, coarse-grained memory map. If we look kind of around this point here, we'll see that our flash memory does indeed go from this address here up to 7FFF. So what that means is that we have 512 kilobytes of flash memory. And what we're going to do is we're going to split that. So normally what you do is you put your program into flash memory, right? You execute your program from flash memory. You can also put data inside flash memory. But yeah, flash memory is generally where you execute from. You can also execute from RAM, but this is one of the ways that you can do this. So what we're going to do is we're going to stuff our bootloader at the beginning of that space, so that this is where the chip is initially going to look for code to execute. So when the STM comes up, and this is actually this can change where it actually looks for the first piece of code. So it has a kind of internal bootloader in that way. We can't touch the internal bootloader, and for all intents and purposes, we will imagine that it's not there. So our bootloader, our code will begin execution here. So we're going to put our bootloader there. And I'm arbitrarily going to decide to split the bootloader into a 32 kilobyte program and leave 480 kilobytes maximum for our main application. Now, it's pretty unlikely that our main application will take up that much space, but this is kind of the potential for what you could do. And obviously you could also divide a bit of space on the end and say, this is where I'm going to store certain pieces of data, or anything like that. But this is the division that I'm going to arbitrarily make. And what that means is that the bootloader will live here at this address, and then it will go up to 800FFFF, and then from 7FFF, and from 8008000, our main application will begin, and that will go up to, let's just fix this here, 887. F. Okay, so how does this actually look when you break it down? So you'll remember from kind of, well, maybe you don't, so this will be a refresher if not, but kind of the way that the program roughly looks when we load it in is that any given program, at the beginning it has something called the interrupt vector table. So we looked at that when we set up our interrupts for the sysdig in quite some detail. But basically there is a piece of there's a table of addresses that lives at the beginning of the program. And that's a fixed size, and each entry in the table refers to a particular interrupt that can happen. The very first entry in the table is actually not an interrupt vector, but rather it's the address where the stack should start in RAM. So that table includes that. And the second entry is what's called the reset vector. So the reset vector is actually the piece of code that is supposed to be your first code that executes. So it's what happens in reset, and when the device comes powered on, that's considered to be coming out of reset, so we would go to the reset vector. And that's what the chip actually does. It goes and looks at that second entry in the table and jumps the execution of the code to that point. So our bootloader is kind of going to look like that. It's going to have its own vector table, and it's going to have its own code and data. And our main firmware is also going to have its own vector table, and it's going to have its own code and data, right? We don't want to have to rely on the fact that the bootloader and the main application have some shared interrupt vector. That doesn't make sense. We want to keep these two programs completely separate from each other. So they're actually going to have their own interrupt vector table and their own code and data. And when we combine them together, what that will look like, and this is obviously not to scale, right, because we know that the bootloader is actually much smaller than the main application, but combined together we'll end up with our bootloader's kind of interrupt vector table and code and data, with some kind of padding in between potentially if the bootloader doesn't take up the whole 32 kilobytes, which it probably won't, but there's also quite a lot of memory. And finally we'll have another interrupt vector table and some code. So if you think about that, we're also going to have to somehow tell the program, like when we actually jump to the main application, somewhere in this code, we're going to have to tell it that this is our new interrupt vector table, because it's, by default, it's still going to look here, because this is going to be at this address, this is where the interrupt vector table is expected to live. And we need to kind of say, no, actually it lives here now. Luckily there is a way for us to do that. So that's something we're going to have to keep in mind. So I hope this makes some sense. It's actually not too complicated. We've just got some different memory regions, all in one big flat memory space. But yeah, we're basically going to execute out of this space when we update the main firmware, so we can write into here. And when we're in the main firmware, potentially we could update the bootloader, but that's probably not something that we will set up right now, or maybe not at all in this project. So we're going to assume that once our bootloader exists and is written to the device, for all intents and purposes now, is kind of a forever thing. Okay, so to make this a little bit concrete, we are going to have to do a couple of different tasks. So first things first, we're going to set up the bootloader. So basically what I'm going to do for that is I'm just going to copy this app directory, and I'm going to paste it, and I'm going to rename it bootloader. So this is going to be our bootloader. And let's also open up a terminal, go inside the bootloader, and you'll notice it also has a make file. It's also got its own linker script. It's got, all the same files as we had before. And I'm just going to run make clean, which is going to remove all of the built artifacts. I'm going to also remove this bootloader O, which was there from testing. That means also in the in here. Of course, I have experimented with this before. So we aren't going to need really any of this other code, so let's just delete this core directory for now. We're going to actually want to share quite a bit of code between the main firmware and the bootloader, and we will actually be setting that up as well. I'm going to rename the firmware .c file to bootloader.c, and in here we can basically just delete kind of all the code we have and get ourselves back to a minimal program here. Okay. Alright, so then the next thing to do will be to go into this make file, because the make file is going to expect that our binary name, the kind of thing we build out of this, is called firmware, and it actually checks the .c file for something with this name. So we're going to change that here. So this is going to be called bootloader. And down here in the expected set of files that we're going to compile, it's just going to be this one for now. Okay, so the first thing I actually want to do is just want to see that this builds. So I'm going to run make, and it does build. We get a firmware object file, we get a bin file, we get an elf file, and we get a map. And then inside the map, this tells us everything that went inside our built file, how this got assembled. And you can see that it basically discarded everything. And we ended up with just a few with our interrupt vector and main program that just returns. So nothing exactly surprising there. Okay. So the code of the bootloader, the thing we're actually going to put into this main file, all we want it to do is to find the address in the main application firmware. So if we look at this this space again, shouldn't have closed it. Go back to this space. We basically need to find the main firmware's interrupt vector table, and we need to find its second entry, because the second entry points to the reset vector for the main firmware. And so that's going to show that somewhere in here there'll be a function that we need to run that's called reset handler or reset vector or something like that. We don't write our own version of that. That is provided by libopencm3, and that will eventually call our main function. So somewhere in here in this code, there'll be a reference up here in the second entry in the interrupt vector table that will tell us where to jump. So basically what we're going to do is just find that second entry, and we know that our main application begins here at 8008000. We know that the interrupt vector table is exactly at that address, and we know that the second entry is going to be, well, we're going to see how we actually get to that second entry. So we need to just basically make our way there, read the address, and then jump to that execution to that address. So it's actually not very complicated. And in fact, our code is going to look kind of just something like this. I'm going to write a function called jump to main. I'm not going to take any arguments. And we'll do something here eventually, but our code is just going to look like this for now. We will never return. We will never return from this function because we're actually just going to change our whole execution to this other space, right? We're never going to actually return from that point. And so what you might realize is that if we do that, right, we're going to call this function. And if you know something about how, function execution and how CPUs work, that means that we're going to push some information on the stack maybe. And, well, in this case, it doesn't matter, because once we actually get to the main application, one of the first things the main application will do, and this is in the reset vector and it's something libopencm3 will do for us, we're actually going to set the stack pointer. So we're going to just remove anything that we happen to have in the stack anyway. So there are no worries about that if that was something you were thinking. So this is going to basically be our code. We just need to fill this section in here. Okay, so I left in here the common defines for now. So we are going to be linked up with this include directory, and that's going to allow us to go and get all the things that we have inside the common defines. So we're going to be able to use things like uint32t. And well, let's think about this. What we need to do is to find the address of the main application. So I'm going to make a define here. I'm going to call it bootloader size. And the bootloader size is 32 kilobytes, which is hex 8000. Right, so this is how many bytes there are going to be maximum in the bootloader. And for the way we're going to set this up in the program, it will always take up this much space, even if we don't use all of it, right? There will always be 8,000 bytes, sorry, hex 8,000 bytes, 32 kilobytes reserved at the beginning for the bootloader, no matter whether we use them all or not. So the main application, the main app start address, we could write it just as, well, we know exactly what it is, right? It's 0800 8000. So we could just write it like this, but I want to keep this somewhat like processor independent. Like, you know, for the most part, this code is going to work if you're using some sort of ARM or STM. This would probably mostly work anyway. But I actually want to kind of make this a little bit independent. So what I'm going to do is I'm going to actually include a header from libopencm3, which will be in the STM32 part, and it will just be the memory map. So what we can say is that the main application start address is the flash base address. So if we go and look at the flash base address, we can see that that is the beginning of Flash, right? And we looked at this before as well, right? We looked all through these addresses and how these addresses are then used to kind of map memory maps registers. So we can have that this is the flash base plus the bootloader size. So this is the very first address of our main application. Okay, so right now this is just a number, right? This is not an address particularly, it's just a number. This U at the end means that this is always intended to be an unsigned number. So if you were to use this in a calculation somewhere and that calculation would implicitly convert that to a signed number, this will make sure that it's always treated as a signed number, so in an unsigned number. So we should probably do that too. It's not a bad idea to do that. So to get a pointer to that reset vector, what we actually need is a uint32, right? We need each entry in the interrupt vector table is 4 bytes long. It's a uint32, right? 4 bytes. And what we can actually do in C is we can create a pointer to the place where that is, right? So this is the type of uint32 pointer. So this is basically something that is an address. It represents an address of the system, and we can use that to read and write from that address. So this is going to be the reset vector. And the way we actually get to that is by kind of turning the main application, this number that we have here, which is just this, we're going to turn that into a pointer as well. We're going to cast it to a pointer. So the way we can do that is to literally just cast the main app address. But as I mentioned, the first entry in this table is not the reset vector, it's the stack pointer. What should become the stack pointer. So we actually need to go to the second entry. And in order to get to the second entry, we can just add 4 to this. And why do we add 4? Well, because each entry in the interrupt vector table is 4 bytes long, right? So this will get us to the reset vector. It gives us now a pointer to the reset vector. So now we want to say, what is the what do we find there? We're going to find an address at this thing, right? It's kind of, we've just created an address that points to a certain place in that table, and the table itself contains another address. So it's kind of pointers within pointers. So the next thing, the next pointer that we need is, well, what's actually inside there? So this is actually going to be, well, this is the reset vector entry, let's say. And the actual reset vector is going to be what we find at this address. So we're going to dereference this using the star. So now we're reading what's at this address. And we're going to convert that whole value back into a uint32 pointer. Okay, and then the tricky part now is how do we then tell the program counter, how do we set the program counter, the instruction pointer, to this address, right? The thing that we have here. Well, we're going to do some magic here. We're going to convert this to a function pointer. So you can see that we are able to do all kinds of casts in C. We're basically able to say, hey, this number here is actually an address, or this address here, no, it's really a number. We can do all these kind of conversions. This integer is actually a float, you know. All of these things are possible. And what we're going to do is we're going to say, hey, this uint32 pointer that you have, it's actually a pointer to a function instead, right? So the value that we find there, the reset vector entry, is actually a function. And to make our lives easier in this, I'm going to create a type definition for this, because the function pointers in C, they're a bit ugly. It's not the best syntax in the world. I wouldn't have done it like this myself. But the way we actually do this is, well, first we say what the return type of the function is. It's going to be void. It's not going to return anything. And second, we have to open brackets, and now I'm blanking as to whether we put this in the beginning or that. I think we do it like this. This is going to be, no, it's not, it's the other way around. Okay, so this is going to be what's called a void function. This is the name of the type, right? So this is a bit strange, but this is actually the name of the type that we're creating. And the arguments to this, right? We can type in the arguments we would take in here. Maybe we would take 2 integers, but we're not going to take any arguments. So what we've actually done here, I guess this is going here instead. Always forget the syntax for this. This is just the syntax for creating a function pointer. So now we've created a type that represents the idea of a function that returns nothing and takes nothing as an argument. So what we can actually do is we can say, hey, this reset vector we have here, it's actually a function. So we can create that void function, and this is going to be our, we'll call it the jump function. This is the idea of converting the reset vector to this function type. And then finally, what we can do is to just call this function. That's it. It's a tricky piece of code, right? This is actually a fairly tricky set of operations, and it's possible that I've made a mistake here, and we'll find that out as we debug it. But basically, just to summarize again, we've said how large our bootloader is. We've calculated our main app address, starting address based on that, based on the fact that we know where Flash begins, we know how large our bootloader is, If we change how large our bootloader is later, we just have to change this define. We've then created a function that when we call it, will actually find the interrupt vector table, which is just the start of flash. We'll find the first entry that isn't the stack pointer, which is our reset vector. Read the address that is in that table, so that becomes the actual address of the reset vector, and then we convert that to a function, or we interpret that address as a function, and we call that function. So essentially what we do is we just jumped execution to that place. And that's it. That's how this should work. I'm going to compile this now. One of the errors that we'll probably get is it will tell me that this should be static. Well, it won't say that exactly, but okay. So the code compiles. That doesn't mean it's correct, but it does mean that there are no syntactic mistakes here. And then let's take a look at this. Let's actually take a look with ls here. And what we can see is that the bootloader we created, the bootloader binary file, is 608 bytes. That's not huge. And it makes sense, I think, roughly for what this should be. You know, we have a large interrupt vector table in the beginning. We have all of the initialization functions, the reset vector itself, the reset function that's included from libopencm3. There are probably a couple of other bits and pieces from libopencm3 that are in there, and then there's our main code here, which is not doing a whole lot. So that makes kind of some sense to me. If we look in the map here, we can see kind of what made it into the compilation. We can see what got discarded, so a lot of things did get discarded from here. We can see that we loaded this up, that we ended up with a few bits and pieces just from the compiler. So the compiler has its own bits of code that it puts in. This is our vector table, so that arrives in the beginning. Then we have our startup main, so this is our main code. And then there is the blocking handler, which is just the thing that we put in the reset vector if we don't actually have a vector to go in there. So it's just all of these things are being plugged into that same address. So these are all of the different interrupt vectors that we can have, or the interrupt service routines rather. A few other bits and pieces. So these are some of the interrupt vectors that are actually set to null, so they don't block, but they just immediately return. We have our reset handler, so that gets put in, some linker stubs, and then everything else is just, yeah, more or less, that's kind of it. You don't have to understand precisely what we just looked at there, but this is just to give an idea, like, it looks about right. Maybe we could look at the assembly to make sure it makes some sense, but let's not do that now. Okay, so the next thing is to actually prevent the bootloader from properly linking when it's larger than the maximum size, right? If we end up compiling a bootloader and it's bigger than 8,000 hex bytes, 32 kilobytes, then it would be nice if it just didn't compile, right? It should never be able to kind of be bigger than that. And we can actually do that, right? We can go into our linker script here. And this linker script is now exactly the same as it is for the application. Linker script is kind of a little language that is used to define how your program will get kind of compiled together. So I'm using the word compiled there, it's the wrong word. Compilation is the process of taking a C file and turning it into some object code. And then there's a second step afterwards called linking, which kind of takes all the different object files, all the different code that lives in those object files, and links them together. Kind of says, well, this piece is going to go here, this is going to go here. And you can imagine that when you generate code, you know, it has an address that says, oh, I'm going to jump 100 bytes forward or 100 bytes back or anything like that. And the linker can kind of make sure that all of those things work out relative to each other when it puts all of the code together. And what we can do with the linker is we can describe kind of what is our program layout, right? We can actually say, hey, we've got memory. We have ROM memory, which is actually our flash memory. It shouldn't be called ROM, but that's our flash memory. It's readable and it's executable, right? We can't write to it. We actually can write to it, but in this case, it's assuming we can't, as in it's not random access. It begins at this address, and we have 512 kilobytes of it. So what we can do for the bootloader is to just say, well, we don't have 512 kilobytes, we have 32 kilobytes, right? And even though there is more flash space, the linker now thinks there is only 32 kilobytes available. Excuse me. So if we had more than 32 kilobytes, this would now fail to execute. And that's kind of all we really need to look at here for now. We're going to need to do some things with the linker for the main application. But the other parts here that basically come into it is we can define our sections. And the sections, we describe kind of how the program then gets assembled together. So in the text section, so that's where the code lives. The first thing we do is we put the vector table, right? We can instruct that there is a place in C, we can say that the vector table, it needs to live in this section. And so the linker will find it in that section, will say, hey, I'm going to put it exactly here at the very beginning of the text section, and this all goes into ROM or flash, right? So then it puts all of the code. It makes sure everything at the end of that is aligned to 4 bytes. And then it puts the read-only data. So that's basically constant data that we have in our program, right? If we have a big table of information that we have, like maybe it contains, I don't know, the value of the sine function or something, right? We don't want to compute it. It takes too much computational power. We put it in a table. Then that's read-only data. We'll never change it. So we can just stick it into the flash memory. And what we've done is to make sure it's aligned to 4 bytes, which means that, it will, when we go to access it, we can access it properly, right? Don't worry too much about alignment for now. And the rest is kind of standard linker stuff that is related more to C++ than it is to C. There's also the idea of putting stuff that goes into RAM but is not cleared on reset. So sometimes you'll want to put things into RAM but you don't want to put an initialized value, and sometimes you'll have things that you want to put into RAM but should have an initialized value, and so you have to put those initialized values into the flash space so that they can be loaded out and put into RAM later. So there's all of that kind of stuff, and then there's the BSS section. I don't remember what BSS stands for. It doesn't have a name that makes any sense, but it's basically variables in your code that should be initialized to 0. So that's what all of that's about. Don't worry too much about this for now. So we've actually set this up correctly, and what I want to do is just try and experiment with this to make sure that it will break if we have a program larger than that. So what I'm going to do is I'm going to create a let's say so this needs to be const, so it goes into flash, uint data array. We'll make it so it's 32 kilobytes long. We'll just say it's all initialized to 0, which is something we can do. So now we've actually put a large piece of data inside our program, which is larger than we can actually account for. So let's run make. And you'll see that it doesn't complain here, right? It didn't crash. And we can go back to the map file here, and we can go and take a look in the map file, and we can see that it just discarded our data here, right? Read-only data, 8000 hex. It just said, I see that you do nothing with this. There's nothing happening in your program. I'm just going to discard it all. To make sure that it doesn't do that, well, there are different ways to do it, but the way I'm going to do it just for now, for illustration purposes, I'm going to just create a for loop. Let's make a uint8x, make it 0, and I'm going to make this volatile. And volatile basically tells the compiler that it can't optimize things to do with this variable. Like volatile is used in the memory mapped IO. So basically, if the compiler sees, for instance, that you write to a variable 2 times, the same value, well, it can say, well, you don't really need to do the second one. I can just do the first one because I know that the value won't change. But if you have memory mapped IO, writing to that address may actually produce different side effects. So volatile will tell the compiler that it shouldn't optimize that way. And then we can just create a, let's make it UN32. I is less than 8,000, I plus plus. And what we'll do is we'll just say x plus equals data at I. Okay, so now what we're saying is that we're going to write to x, we're going to use data, and it can't optimize this away. So basically what that also means is it can't optimize data away. So let's make that. And what we get is an error that says bootloader elf section.txt will not fit into region ROM, which is exactly what I want to see there, right? I want to get a compiler error that tells me our program's too big. So excellent, that works. We can get rid of these bits and pieces because we know that that's good now. So that works correctly. The next thing that we need to do is to pad the bootloader to the maximum size. So there are different ways of achieving this, but basically what I want to do is I want to make sure that this bootloader.bin, which is just the raw binary representation of what needs to go into memory for a microcontroller, I want to make sure that this is always 32 kilobytes exactly. Because that way, in the main application, we can just take this raw blob and put it as the very first thing in memory. And that way, we know that everything will be properly set up for the bootloader. So I want to write a little script that will pad the bootloader to the right size. So I'm going to write that script in Python. I'm going to arbitrarily choose Python. I think most people have Python installed. We could choose anything. If you're playing along at home, you can choose whichever language you like for this. So I'm just going to call this pad bootloader.py. And how are we going to do this? Well, first of all, let's just note the bootloader size, which is 8,000, and the bootloader file, the bootload file. The bootloader file is going to be at bootloader.bin. Okay. And we're going to open the file. So with open bootloader file, and we're going to read that as a binary file, as f. The raw file is going to be f.read, so it's going to read the whole file. And then what we can say is the bytes to pad is going to be the size of the bootloader minus the length of the raw file. So keep in mind that if the bootloader bin was larger than 32 kilobytes, it wouldn't even compile, right? So we're assuming that it is less than 32 kilobytes. So this operation won't produce a negative number. And the padding is then just going to be, notice that the raw file is of type bytes, right? So we can create raw bytes this way as well using the bytes function. We could do something like this. This would create a bytes object. What we're going to do is we're going to pad this up with some bytes, and we just want to put FF for every byte that is not that has to be padded. FF should go in that place where it's blank, right? So FF for nothing in range bytes to pad. So this is just going to create a byte array for us of bytes to pad length. So this could also be 0, by the way. If it's exactly 32 kilobytes, then padding will be 0. There'll be nothing in it, and that's fine. So now we're going to with open the bootloader file, but this time for writing as a binary file. We're going to do f.write, and we're going to write some bytes to this, and that's just going to be the raw file plus the padding. So let's try to execute this now. So I'm going to run python pad bootloader, and then I'm going to do ls with the b, and we can see that our bootloader is now exactly 32 kilobytes, right? That's exactly hex 8000 bytes. Perfect. All right, so now what we want to do is to have this happen automatically when we run make. So let's go to the make file, and we will scroll down to where it's creating bin files. So we're only creating one bin file here. This make file is actually way overkill for what we need. But we're going to create a bin file that takes in our elf file, and it uses the object copy command to extract the bin. If you've seen my RISC-V series, you'll have seen that we do the exact same thing there as well. So what we're going to do here is we're going to run this program, python pad bootloader.py. Okay, so I'm going to run make clean, and I'm going to run make. And you can see here it actually logs out this command, because this bracket q thing, that actually means to silence the command. So we'll put that up there as well. But what we should see is if we do ls here, we actually have a 32 kilobyte bootloader. And let's just take a quick look in Bewitched at the bootloader.bin. So here we can see this is the vector table. You can see this is the big list of addresses. These are in little endian format. So this first one is the stack pointer address. And because it's in little endian, you need to reverse the bytes. So it's 2001 0800. So that's a RAM address, right? We know from the linker script that RAM begins at hex 2 million, right? So that's a RAM address. That makes some sense. Okay, then this is the reset vector. So let's take a look at that. So what is that? That's 080001C1. Okay, that seems to make sense to me. And if we can confirm that by looking in the bootloader map, and we can have a little look at the reset vector function. So our main code is here, but the reset vector, which is here, that is at 0800001C0, and that is what we see here, right? Or 1C1. And actually the reason that this is 1C1 is to do with the mode of execution of the ARM CPU at that point, right? So it uses addresses should always be aligned to 4 bytes, which means we should actually only ever see 0, 4, 8, and so on there. We shouldn't see 1. And what it means is that the 1 can be used to indicate something else. So that's actually indicating the execution mode. So thumb execution or ARM execution. So that's what that means. That's why it has a 1 at the end there. Okay, so that looks good. And if we take a look at the rest, we'll see that they are, for instance, this address, which is 080001BF. And that address, if we look, I'm just going to search this in the map file, which I think will be an easier way of doing it. So BF, yeah, and of course it's offset by 1. So presumably this is going to BF, which means it would be BE, which means we're going to this null handler, right? So everything in these other addresses are the null handler, and there are probably some that have this blocking handler, right? So if we found a little bit further down, some of them would also have BC or BD rather, we'll see here. Yeah, okay, good. So that is the code there. Eventually you can see we start to get to something that looks different from all of this big table. This is where actually code begins. And this makes some sense probably. So some of the actual code which goes into this, so 1AC, well, this is then the beginning of the main function. So the main function is going to begin here at this point, I believe. Yeah, so this is where the main function begins. So this is actually just the code of main. And we could see for any of these things, this would be where the code is. All right, so that looks good. This all wasn't strictly necessary, but it's good to this is kind of some of the tools you can use that if these things don't work straight away, you can kind of try and apply some of this logic and see, well, maybe this is why it isn't working. All right, so now we can pad the bootloader. We're kind of done with the bootloader for now, until we come to test it. Now we need to turn our attention to the main application. So first things first, we need to somehow include this binary blob inside the main application. Well, there are different ways we could do that. We could, technically, I think you can use the linker script for this. You can just sort of tell it to link a raw binary file. I tried to do that a while ago, and I wasn't able to make it work in a straightforward way. But thankfully, there is kind of an easier way of doing this, and that's kind of just to, take advantage of the whole system that we have already in place and just sort of put it into what's called an object file. So every time we compile a file, a C file, or actually kind of any file, a C++ file, a C file. I'm pretty sure if you do this in other languages, you also then create object files, because object files are really just ELF files. They're just the executable and linkable format. So it's basically just a container for some code and some data and some sort of some bookkeeping information about what's there and how to offset it and that kind of stuff. And these files are consumed by the linker to put things together. So what we could do is just try and get this bootloader bin, just try to get it into an object file. And of course we already have an object file down here, bootloader.o. And that may work, just taking that object file and linking that in, but I'm not entirely sure if it would. So what we're actually going to do is we're going to create a file inside source here, and I'm just going to call it bootloader, and it's not going to be .c, it's going to be .s. S is the extension for assembly in this, in this context, right? This is the .arm assembly extension. But we're not actually going to write any assembly. We're just going to take advantage of one of the features that the assembly language has, which is it has a couple of directives for being able to just include a binary file. So that directive is literally just .inc bin, and then we can provide a directory of where we can go to find a bin. So we basically just want to point at bootloader.bin down here. Now, it's a little bit weird. I'm going to put this in the source file. So we're going to go, you would think that, say, if we were to do this, we would need to go back one directory and then back another directory into bootloader and then to select the bootloader bin. But this is actually kind of ends up being relative to the linker script. So we need to just take away one of these. So this is now a file. If we compiled this, it would just contain just this blob, but inside an object file. But the thing we actually want to do is we want to make sure that we can tell the linker to put this in a really specific place. So the way we're going to do that is we're going to place this into a certain section. So we can use another directive which says section, and we're going to call this section the bootloader section. I can't spell bootloader. I may actually call this bootloader section, just to make this really clear that it's not anything else. Okay, and this is kind of, that's our magic way of wrapping that up. So if we come out of the bootloader section into the app and run make, what we should now see is that we have a bootloader.o. No, we don't, because we need to add it to the make file first. So let's do that. It's actually in this part. So this is going to be the bootloader .o. And basically the make file knows how to compile assembly files. So it knows how to see an object file and, how to create an object file from an assembly file. So it knows how to do that. So when we run make, now we get the bootloader.o file. Great. Okay, so what we're going to do is now go into the linker script, and it looks exactly the same as the bootloader did, right? Except before, we changed this to be 32K. Now we actually are going to leave that as it is, because we do actually have 512 kilobytes. But the change we're going to make is we're going to come down to this text section, and instead of saying that the vector table should be the very first thing that goes into memory, well, instead what we're going to do is to say that the bootloader section, that this should be the first thing that goes in. Now let's try that out. Let's run make. First run make clean just to make sure. Run make, and let's take a look at the map. And of course the map, it tells us what gets discarded, so let's just see. And unfortunately, our bootloader got discarded. So why did that happen? Why did our bootloader section get discarded? Well, I think what the linker sees is that nothing else refers to this section, and therefore it can kind of optimize it out. So what we can do is we can use this keyword here, keep, just to make sure that it doesn't discard that. So let's wrap that up in a keep. Let's run make again. Let's take a look at the map file again. And hopefully that bootloader part has disappeared. So I see that the bootloader O, it has some parts here, the text, the data, and the BSS, but the bootloader section, that has not been discarded. So that part, I think if we search for that bootloader section, we'll see that that indeed did make it into the final application, and that it is 32 kilobytes, and that it is directly before the vector table. So that is perfect. And let's just double check that first by opening again Bewitched and open up the firmware.bin. So what we should see now is that this should be the bootloader. And we can actually confirm that quite easily, because if we look at one of these addresses, well, this is going to be the reset vector for the bootloader. I don't know what I did just there. Sort of changed the, removed all the color somehow. Really not sure what I did there. Yeah. So this this address here, which is again 080001BD, right? We know that this address lives inside the bootloader space because the main application space starts at 80 0800 8000, right? And this address is less than that beginning part. So we know that that's part of the bootloader. And then we can scroll down through a bunch of this stuff. We can see that that's where the code is. Then we get all of our padding. And that padding is going to go on for quite a while. So let's just jump down to hex 8000. Sorry, hex 8000. And now what we see is that at hex 8000, now we get the beginning of the main application, right? We see that the padding ends and then the main application begins. And then we have this address as the reset vector, which is 08008905. And that does indeed live in main application space. So great, all of that looks good. Now, we're not done. If we were to actually compile this now, it would jump to our application, but it would very quickly break. And the reason that it would break is because of this thing that we talked about earlier. which is that our code is going to start running here. We're going to run our bootloader, which is just going to immediately jump down here, do some execution. But very, very quickly, our code will begin to receive interrupts, right? We've got interrupts coming in from the systic to tell us that the systic is operating, right? And we're supposed to increment a variable. Well, that's not going to happen. What we want to do is we want to jump then to find the address of the systic handler here, jump somewhere down here, execute that, and jump back. But what we're going to do, in fact, is we're going to look down here for the address of the systic handler, and we're going to jump in here somewhere, and then that's going to be the wrong place. That's probably just going to either block or do nothing, and so our program won't work correctly, right? We won't see our ticks incrementing, and we won't see our light blinking in the right way. So we need to tell the main application vector table where it now lives. So that's the next step. Let's go into firmware C, and I'm going to bring in another libopencm3 library header, called SCB, I think. SCSBC. It's in CM3 because it's actually not part of STM32. It's part of the all ARM chips. So the SCB. Okay, and what we actually need from here is something called the vector table offset register. So of course there is actually just a register in memory. Well, there's a register as part of the chip that allows us to tell it where the interrupt vector table is located, right? And it's exactly for this purpose, because people often have multiple programs living in the same space, right? And we jump to different programs there. So we need to be able to change where our vector offset table, our vector table offset is. So this is actually going to be as simple for us as coming into the firmware and stating the well, let's just define the same thing again, which is just going to be bootloader size. 1000. Right, so we have the same define in both. We're going to move that to a common location very soon. Let's write a function here called vector setup. And what we're just going to do is to write to the SCB vtor register. We're going to write to it that we're offset by bootloader size, right? We're just like before the offset of that register is 0, right? So it's just going to look in the normal location, which is hex 08000000, and we're going to offset by bootloader size. So let's make sure that that is the first thing we change before we change anything else. And that's it. So if we now run this code, so let's run make, and then let's debug this application. So I'm running the debugger. I'm going to let it execute. And what we actually see, and it's a little bit light in here, so you may not see this, but what we see is that, yes, indeed, that light is blinking. I think you should see that. And it's blinking using PWM, which is something we implemented in the previous episode. But that's great. That means that we went into the bootloader, we jumped to the main application, and we began successfully executing the main application after relocating the vector table. And if we hadn't relocated the vector table, this wouldn't work at all, because we actually make use of our system get ticks, which is telling us how much time has passed, to actually change the duty cycle of that LED. So if we were to comment this out and then run this code again, what we will see is that nothing happens on the chip. Nothing changes with our LED. And our code is running. I can put a breakpoint down, But the problem is that system get ticks is just always going to return 0, right? We're going to look at ticks and it's always going to be 0 because nothing ever calls this function to increment it. And of course you can't see that, but I just put a breakpoint down here. I jumped into this function and ticks actually is always at value 0. Okay, so that hopefully makes some sense. And I think we've covered all of the main things we need to do here. Okay, so what we did here today was we wrote a kind of bootloader, but that bootloader really didn't do anything special. It's basically added a sort of stepping stone on the way to getting to the main application. But what we actually have done now is to already divide the project in two, to compile two projects separately. We've changed the linker to actually allow us to put the bootloader into the main application itself in a predictable way. And we've made sure that the main application understands that it lives at a different place in memory to where it probably thinks it should, based on the fact that it isn't actually the first thing that executes anymore. In the future, we can start to build on this concept to actually write a bootloader that is able to upload a new firmware. In order to do that, we're going to have to do quite a lot of we're going to have to write quite a lot of code. We're going to have to write code to control the flash, so we're going to have to be able to tell the flash base that we want to write code there. We want to write data to the flash, because by default, if you just try to write to the flash base, it won't do anything. So that's something we're going to have to do. We're going to have to write a UART driver. So we're going to have to set up the UART peripheral, which is our serial interface. The serial interface is going to be the physical medium by which we transfer information from the computer to the board. That interface could actually be replaced with anything, right? So we could replace that as long as we have a driver that is able to transfer information from one location to another, we can replace that interface with whatever you want. So the UART layer can eventually be replaced by an Ethernet layer or a wireless layer or a CAN layer or whatever you want to actually do to do the information transfer. Because on top of that, we're going to build our own protocol for exchanging information, a packet format, and use those packets to actually send the data. And then eventually, we'll send the data, we'll have a kind of state machine that runs this whole thing, and we'll be able to write the new firmware. And then eventually in the future, when we get to that point, we'll do all of the authentication and the cryptography stuff to actually make sure that the firmware that we get sent is signed. And if it's not signed, then we won't jump to it. So that's kind of where we are. I hope that all of this has made sense. If it hasn't, please leave me a comment below asking a question. You can also join the Discord server and ask any questions you might have there. But until then, and until the next video, thanks for watching, and I'll see you next time.